Hello, everyone. In this video, we are going to look at example 1 from section 2.8 on using derivatives to evaluate limits. So the reason why we are calling this section 2.8 and visiting it now is because it's situated after learning about rules of derivatives, but its contents is about limits. So in this entire section, we learn about how to use derivatives to compute a certain type of limit. So to get things going, let's look at the function that we have written here. F of x equals x squared plus 1 over x squared minus 1. The graph of this function is drawn on the set of axes here. So now we're just going to look at some limits dealing with this function. So first, let's evaluate these limits by just looking at the graph. So let's do the first one together. Then I'd like you to do the rest of the parts and then check your answers. So for part A, the limit as x goes to infinity of f of x. So for that, what we want to look at is the x-axis. And now we're taking x, or the input, going to infinity. So it gets larger and larger. So it looks as if the function value as x gets larger and larger approaches 1. So we'll put 1 here. So now looking at the graph, try to determine the other limits that you see written here. Please pause the video and work out those estimates on your own. So here are the limits looking at the graph, and I'll just say a few things about some of these parts. So let's look at, say, part C together. So part C, we're looking at x approaching -1 from the positive direction, so from the right side. So we can look for -1 when x is -1. And we're going to approach x from the right side. So we're going from this direction. So if we notice our graph, where are we on our graph? Well, we are down here. And as the input approaches -1, rather, from the positive direction, our output, it looks like, gets further and further negative. So that's why we see the limit here. It looks like -infinity. And in fact, if we want to decorate this graph a little bit more, it looks like we have some asymptotes on various locations of our graph. So recall, an asymptote is a axis or a line in which our graph approaches but never touches. So it looks like we have some asymptotes here. Okay, so that was just using the graph. Now let's just recall how we would attack or compute or find those limits using just the function. So this is a bit of a review for us from our first chapter. But recall that the approach using the function, using f of x as written, would be to use a table. And the reason why we'd have to use a table is because this function is unique in some that we've looked at, because there's nothing that cancels when we try to plug in a value for x. And we see that because the denominator, it can factor as x plus 1, x minus 1, but the numerator does not factor. Okay, so let's set up a table, and I'll get you started, and I'd like you to finish it on your own. So let's look at x values compared to the output values of f of x. So x squared plus 1 over x squared minus 1. And in this table, we're going to look at certain values of x and then see what happens in the output. So for part A, let's do part A using the function. So part A, we're looking at x goes to infinity. So what we want to do then are plug in values of x that get larger and larger. So say we could start with 5, maybe go up to 10, maybe 100, then maybe 1,000. So let's see what happens to the outputs as we increase our inputs like this. So we can look at, well, what happens when x equals 5? What is f of 5? Well, f of 5 is going to be, when we plug it into our function, 5 squared plus 1 over 5 squared minus 1. So we get 25 plus 1, which is 26, over 25 minus 1, which is 24. And we can compute that on our calculator. 26 divided by 24, and we get 1.08. So we get 1.08 here. So now what I'd like you to do is find the outputs for the remaining 3 inputs that I have listed here. Please pause the video and then compare your work. All right, so for our corresponding outputs, we should be getting 1.02, 1.0002, 1.000002. So as we see what happens to the output as x approaches infinity is we get 1. So the limit here, the function value approaches 1. So we could conclude from the table here that the limit is in fact 1. So now let's just do this one time with one other limit. So let's look at E here. So E, we're taking the limit as x goes to +1 from the right side. And we see that it looks like our function goes to infinity. So what does that look like if our outputs or our function goes to infinity? Well, we can use the table again. So we're going to look at input values compared with their f of x values. So what are the input values here? Well, again, we're looking at x going to 1 from the positive direction. So that means I'm going to start out here at a number farther, a little bit farther away from 1, and then get closer and closer to 1. So my test values I'll want to use, maybe I'll start with 1.1. Then I'll go with 1.01, get closer to 1 there, 1.001, and maybe 1.0001. So I test, as you see, the test values I use are values close to 1, but then get closer and closer and closer. But these numbers are approaching 1 from the positive side. All right, so then we just need to look for those outputs. So we compute f of 1.1 first. So using our function, that would be 1.1 squared plus 1 over 1.1 squared minus 1. We can compute that on our calculator and we should get 10.5. I did this ahead of time. That's why I'm getting these answers so fast. Okay, so now I'd like you to pause the video and compute the remaining 3 output values for those values of x I have listed here. All right, so compare the answers here to what you have. And then notice what do you notice about the output values as we have input values closer and closer to 1? Well, the output values, they blow up, they get larger and larger. So we see here that for part E, our function does in fact approach infinity. In this video, we're going to look at example 2 from section 2.8 on using derivatives to compute limits. So in example 2, we are prompted to use a table to estimate the limit as x goes to 0 of sine of 2x over 3x. Then we're asked, is it possible to find the exact value of the limit? So first, let's look at this table together. So in our table, we're going to have our inputs, x, and then our output, sine of 2x over 3x. Now we want to look at what happens to the output values as our input, x, gets close to 0. So I can draw a little picture of an axis for us. So we want to approach 0 here. So maybe I'll start with 1/2 and then get closer and closer and closer. So I'm going to use the numbers 0.5, 1/2. And I'm going to get closer by going 0.1, and then even closer 0.01, and even closer 0.001. And we'll see what happens with our outputs. So for this table, to compute the corresponding output values, I just plug in my test value, or like 0.5, into my function. So let's do that together so we can see what that looks like. So we get sine of 2 times 0.5 all over 3 times 0.5. So that, when we compute 2 times 1/2, we get sine of 1 over 3 times 1/2, we get 1.5. If I go to my calculator, I can compute that we get around 0.561. So the output here is 0.561. So now I'd like you to pause the video and finish filling in this table on your own, and then compare your answers with the video. All right, so for 0.1, we should be getting 0.662. 0.01, our output is 0.667. 0.001, we get that same output. So we see here that it looks like the sine of 2x over 3x approaches 0.667, or 2/3, as x approaches 0. So now let's look at the follow-up here. It's asked, is it possible to find the exact value of the limit? Well, one way we saw computing exact values is to plug in the value that we are approaching. So x is going to 0, so can we plug in x equals 0? Well, let's see what that would look like. That would be sine of 2 times 0 over 3 times 0, which 2 times 0 is just 0. So we'd get sine of 0 over 0. Uh-oh, this isn't looking good. Sine of 0 is 0, and dividing by 0, well, and then the denominator here is 0. So we have something that looks like 0 over 0. So what's interesting here is that, recall, we're looking at x approaches 0. So when we're looking at the limit, we're not looking at exactly these zeros, but what are the trends of the numerator and denominator? And it turns out there are many different limits that can result from a form that looks like 0 over 0. So we can't plug in, no go. But we can use a method called L'Hopital's rule. And it's spelled like hospital often, or using another language or another spelling, L'Hopital. L'Hopital's rule. The original spelling of L'Hopital's name included the S, but French spellings removed the S and instead added this accent, which is called a circumflex. So there's a little history for you as well. All right, but let's get into the rule. So L'Hopital's rule says that if we want to compute the limit of a function that has this form here, meaning that when we actually plug in the value, we get something like 0 over 0, then the limit that we want to compute, so in our case, limit as x goes to 0 of sine of 2x over 3x is equal to the limit as x goes to 0 of the derivative of the top over the derivative of the bottom. Super cool. So that will often simplify functions to allow us to plug in the value that we are approaching and to get a legitimate answer, or to get a number rather than an indeterminate or a 0 over 0 form. So what would that look like for us? Well, the derivative of sine here is cosine. We need to do chain rule, cosine 2x times 2, derivative of the inside, over derivative of 3x is just 3. So we can see here, this would become, we can just plug in 0, 2 times 0 times 2 over 3. 2 times 0 is 0, and cosine of 0 is 1. So this becomes 2 over 3. And we see that that does indeed match up with the value that we saw our table approaching. We'll just go ahead and circle that here. So the value that we found from our table was 2/3, and that is also the value that we're getting for the limit using L'Hopital's rule. So let's take a moment to chat a little bit more about that rule. So on the top of our next page, we have a summary of when this rule can apply and what it means in a formal definition. So there are 5 basic, what's called indeterminate forms in which L'Hopital's rule applies. So we saw the 0/0 form in the second example above. This rule also applies when our function evaluates to infinity over infinity, negative infinity over infinity, infinity over negative infinity, or negative infinity over negative infinity. So in all of these cases, we can use L'Hopital's rule. So what does that rule say? Well, it says, suppose we have 2 functions, f and g, that are differentiable. That's important because we're going to use the derivative when we compute the limit. And the derivative is not 0 near the value that our x is approaching, except possibly at 0. Then if the limit as x goes to a of f over g has one of the 5 indeterminate forms above, then the limit of the quotient, or the limit of f over g, is equal to the limit as x goes to that same a of f prime over g prime. So a couple words of caution here, or notes of caution rather. To use L'Hopital's rule, your limit must be in one of the 5 basic indeterminate forms above. So it's really tempting to just, when you see a bunch of limits that you are taking of quotients, to just use L'Hopital's rule everywhere. Turns out sometimes those functions do not have one of these forms, so we cannot use L'Hopital's rule. So only when we have one of these forms. So it's really important that you need to check. And you check if your function has one of those forms by plugging in the value that you want your limit to approach into the numerator and denominator and seeing if you have one of those forms. And then 2, there's actually a few more forms, or indeterminate forms, that we can use to apply L'Hopital's rule. So they look like 0 times infinity, 0 times negative infinity, infinity minus infinity, 0 to the 0, and 1 to the infinity. So again, these are forms of what our function might look like if we plug in the value that we are approaching. All right. Thanks for listening, everyone. In the next example, in the next video, rather, we'll look at another example of using L'Hopital's rule. Thanks for watching.